Welcome viewers back to Juddy Productions. In today's video we're looking at Year 10 Physics. The section is Section 3 Motion. Our topic is motion graphs and the skill for today is analysing and evaluating a velocity time graph, and this is example number 1. So let's jump into it. So question number 1, what was the acceleration of the object over the first 2 seconds? So we're looking at this red section of the graph starting at a time of 0 all the way up to a time of 2. And we want to calculate the acceleration during this particular first 2 second period. We know that the acceleration is equal to the gradient of the graph, which is calculated from the rise over run. So first of all, we can see in the graph here that we've risen from our starting time of 0, we've risen from a speed of 0 all the way up to a speed of 40. So that has a rise of 40 meters per second. And run along the x-axis, we've started from a time of 0 and we've run across to a time of 2. So the rise over run is 40 meters per second divided by 2 seconds, giving us an acceleration of 20 meters per second forwards. Now we say forwards because on this graph the velocity hasn't got a direction of north, south, east or west, so if the line is above the x-axis, we'll just call this a forward direction. So the acceleration for the first 2 seconds is 20 meters per second forward. Question number 2, what was the acceleration of the object over the final 2 seconds? There's our final 2 seconds. We're talking about motion from a time of 5 across to the time of 7 seconds. So again, the acceleration is equal to the gradient, which is equal to rise over run. So in this case, we don't actually have a rise, we have a fall. This is a downward slope. So it's fallen from a velocity of 40 meters per second at a time of 5 seconds, all the way down to a velocity of 0 at a time of 7 seconds. So really, it's not a rise, it's a fall. But we'll put that in as a rise of negative 40 meters per second. And the run, of course, from 5 seconds to 7 seconds is 2 seconds. So the gradient is rise over run, negative 40 meters per second divided by 2 seconds. So that comes out to an acceleration of negative 20 meters per second squared in a forward direction because, again, the graph is above the x-axis. However, because the acceleration has a value of negative 20, there is an alternative way to describe this as well. So an equally correct notation would to say the acceleration is 20 meters per second in a backwards direction. Negative acceleration forwards is the same as positive acceleration backwards. Question number 3. What was the distance traveled by the object over the entire journey? So the distance from a velocity time graph can be calculated from the area under the graph. That is the area between the line and the x-axis. In this case, it happens to be the shape of a trapezium. Trapeziums can be identified as having 1, 2, 3, 4 sides, 2 of which are parallel, such as the top line at 40 meters per second and the bottom line at 0 meters per second. They are parallel in direction. So here's an equation we can use to work out the area of a trapezium, where A represents one of the parallel side lengths, B is the other parallel side length, and H is the height of the trapezium. So in this case, we have a short parallel side length of 3, a long parallel side length of 7, and a height of 40. Putting that into our equation, we end up with a distance of 200 meters. So this graph represents a distance traveled of 200 meters. Question 4, what was the object's displacement at the journey's end? Well, this is a rather simple question, carrying on from question number 3. As the graph is always above the x-axis, that is, the line is always well and truly above the x-axis, the displacement is equal to the distance traveled. So displacement is equal to distance. So it has traveled 200 meters forward. Question number 5, what was the object's average speed of the entire journey? Quite simply, speed equals distance over time. We just calculated the entire journey traveled a distance of 200 meters, and from this graph we can see the entire journey took 7 seconds. So 200 meters divided by 7 seconds gives us approximately 28.6 meters per second. Question number 6, was the object ever stationary, and if so, when? So no, the object was never stationary. During the first 2 seconds, it's accelerating. During the next 3 seconds, it has a constant velocity. And during the final 2 seconds, it's decelerating. This object was always moving, never stationary. Question number 7, during what time interval or intervals, if any, was the object traveling forwards? We've really addressed this question earlier. The object was traveling forwards for the entire duration of the journey. That's because the line is always above the x-axis. This line is always above the x-axis, representing a forward distance. during what time interval or intervals, if any, was the object travelling backwards? Well, this is kind of answered by the last question as well. The object was never travelling backwards for the duration of the journey. The line was never below the x-axis. If we wanted this graph to represent distance travelling backwards, our line would need to drop below the x-axis. This would indicate backwards distance. You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.